Hello, everybody. Welcome to our final big unit. We might do a little bit more after this, depending on whether you're taking honors or CP Chem. And we've got some labs and stuff to do, but this is the real sort of last big unit that we're going to talk about in this remote learning nightmare that we are all in together. Oh, can't wait to get back into the classroom with you guys. Okay, so in this unit, we're going to start quantifying amounts of chemical substances and specifically amounts of substances involved in chemical reactions so that we can get to this place where, if I want to make X amount of, fertilizer at my fertilizer plant, how much nitrogen am I going to need in order to make that much product? It's a really, really important question that scientists need to be able to answer. Not just scientists, but pharmaceutical companies, materials manufacturers, pharmacists, anybody who's making anything with a chemical reaction. So you're going to need a calculator for this, and hopefully you've got your Unit 6, the mole and stoichiometry packet handy. If not, pause and go get that now. And we're going to start with a conversation about counting numbers. So in order to count up amounts of substances, whether they are donuts or years or shoes or pieces of paper or atoms, we need counting numbers. And you guys are familiar with the counting numbers for donuts being a dozen, with years being maybe a century or a decade, with shoes coming in pairs, and with paper coming in what we call reams. You probably have never heard of that because you haven't had to order bulk paper. But a ream is 500 sheets of paper. What we're going to need for chemistry is a counting number just like that. Because counting up individual atoms one by one is pretty silly because atoms are really, really small. So we need a really, really big number in order to get a reasonable amount of a substance. So the guy that figured that out, that handsome devil on the left, is Avogadro. And Avogadro came up with the counting number that we use in chemistry called the mole. So not an animal mole, a mole is the counting number. And that number is 6.022 times 10 to the 23rd atoms. So if you have a mole of anything, that's how many atoms you have. Now, where did Avogadro get that number? He happened to decide to base it off of the number of atoms in 12 grams of carbon-12. Picking carbon-12 because it's very stable, non-toxic, found in all living things, pretty easy to work with in the lab. And so carbon was our basis for this number. Let's take it to our notes, shall we? Oops, I'm not in the place I want to be on the notes, you guys. I have this random squiggly mark I made to test my pen out. Let's see if we can erase that. And this isn't even the right part of my notes. I want to be. Oh my God, I made a squiggly mark over here too. It's A+ video work here by your chem teacher. All right, here we go. Now I'm ready. Now I'm ready to talk. All right. What were we saying? We were saying that the mole is our chemistry counting number. So that's just, I think you already got that description written up at the top of your page for you. This is chemistry's counting number, just like you would use dozens for eggs or for donuts. We're going to use these for atoms or molecules or units. So atoms if we're talking about elements, molecules if we're talking about covalent compounds, and units if we are talking about ionic compounds. So the mole. A counting? No. Let's be more formal than that. This is the SI, remember System International, the SI base unit for an amount of a chemical substance. My desk is like really squeaky, you guys. I hope you can't hear it on the audio. Ugh, my handwriting's all over the place too. Okay, the SI base unit for an amount of a chemical substance, and that number is 1 mole is equal to 6.022 times 10 to the 23rd particles. I'm just going to use particles because the word particles is a generic word that can mean atoms, molecules, or units. Okay, so that is Avogadro's number. Now, because when we are doing chemistry problems and we want to be able to work in this unit of a mole, we're going to need to be able to convert sometimes in between moles and particles or particles and moles, just like we would convert, days into weeks or, numbers of eggs into dozens. These are conversion factors that we used way back at the beginning of the year during dimensional analysis. So this right here, Avogadro's number, is now another conversion factor for us to work with. And frankly, oftentimes we just work with 6.02. We drop that other 2 times 10 to the 23rd. Just make our life easier. We'll just go with 3 sig figs. Okay, so let's practice using Avogadro's number as a conversion factor. The question is, how many atoms are there in 3 moles of copper? Remember, when you're doing dimensional analysis, you always want to start with your given value, 3.00 moles of copper. Now I'm going to say what the substance is because this is chemistry class and we care what the substances are. However, in addition to that, it's going to be really important when we start working with mass. Okay, so now I'm going to multiply by my conversion factor. Remember, we want our units to cancel top to bottom. So my 1 mole of copper is going to go on the bottom. And if I have 1 mole of copper, that means that I have 6.02 times 10 to the 23rd. I'm going to use the word atoms here because I'm talking about an element of copper. And now, of course, I need to calculate. And so here on my calculator, you guys, first we're going to turn my calculator on. I want you guys to remember a magical button that we use on this calculator to do exponents. So here we're going to go. We're going to go 3 times 6.02. Now, I don't want you to do times. I don't want you to do 10. I don't want you to do caret. None of that. Because if you don't use parentheses, your order of operations are going to get messed up. So to get that exponent of the 23rd, we're going to go 6.02, and you're going to hit your EE button. For me, that's a second EE. See how that 1 E pops up? That means times 10 to the, right? So that's my exponent, 23. It's all I got to press. I don't need parentheses, I don't need a 10, and I don't need a caret. Just EE 23. There's my answer. My answer is, let me see if I'm going to still have room here. Maybe I'll write my answer a little bit down below. My answer is, and I'm going to want 3 sig figs in my answer. My answer is 1.81 times 10 to the 24th atoms of copper. Okay, so you start with your given value, you plug in your conversion factor, you make sure you round to the correct number of sig figs, units, and a substance in your final answer. And remember, your units are canceling top to bottom. Let's do another problem. Let's say this time we're starting off not in moles, but in particles. This time I'm given 4.12 times 10 to the 21st molecules. I'm going to abbreviate molecules as MOLEC because I don't want to confuse it with the mole, which is MOL. This many molecules of carbon tetrachloride. It wants to know how many moles I have. Well, this time, I want my molecules to cancel, and I want to convert into the mole. So this time, my 1 mole of the carbon tetrachloride goes on the top, and Avogadro's number, 6.02 times 10 to the 23rd molecules of CCl4 are in 1 mole. So here you can see my molecules are going to cancel. And now I will be in moles of carbon tetrachloride. So back to my calculator. Remember that magical EE button. Clear that out. 4.12 EE 21. Now I don't really need to multiply by 1 because it's just 1. So then I'm going to divide by the denominator. So divided by 6.02 EE 23. 0.00684 moles. 0.00684 moles of carbon tetrachloride. Shall we do another? This time the question is asking us, how many hydrogen atoms are there in 1.5 moles of water? So there's a little extra step to this one. Start with your given value, 1.50 moles, and this is why it's important to write the substance, H2O. So the first thing I have to do is I have to turn those moles of water into molecules of water using Avogadro's number. I know that 1 mole of water, so that's going to go on the bottom so I can cancel it out, contains 6.02 times 10 to the 23rd molecules of water. My moles of water cancel. Now, if the question was asking how many molecules of water would I have, I'm done. But that's not what the question's asking. It's asking how many total atoms of hydrogen. So now you actually have to look at what a water molecule looks like. And you know that there's 2 hydrogens and 1 oxygen in every 1 molecule of water. So I'm just going to add in one little conversion factor here that tells me that 1 molecule of water contains 2 atoms of hydrogen. Right, so I basically just had to take my answer and multiply it by 2 because a water molecule looks like this: hydrogen, oxygen, hydrogen, right? So if I have X number of those things and I want to know how many hydrogens total, it's a 2 for 1. And so to my calculator, to calculate how many hydrogen atoms that is, I'm going to go 1.5 times 6.02 EE 23. Oh, times 2. Almost forgot. My answer is 1.81 times 10 to the 24th. 1.81 times 10 to the 24th atoms of hydrogen. Again, I went with 3 sig figs here because there's 3 in my given value. So just trying to be consistent. 3 sig figs here because there are 3 in my given value. Remember, your conversion factors don't count towards your significant figures. Okay, so I think I would like you guys to pause here with the notes that are on page 2. And I would like you to pull out that secondary resource that I asked you to print out called your mole map. The mole map is something that we're going to use to help us keep track of all of these different conversion factors that we're about to learn that take us into and out of the mole as our counting unit. So I'm just going to go ahead and scroll to the bottom of my page here where I left myself some space for the mole map. Okay, so the mole map looks like this. On one part of your mole map, on the left-hand side, let's just stick with the left-hand side for now, you guys. The left-hand side says mass of substance A, and there's like a road leading towards the moles of substance A. And there's a road that goes down here leading us into, whoopsies, oh boy, it's not the best rectangle. All right, so down here, particles of substance A, and then going up north to volume of substance A. Okay, now don't worry about this other half of the mole map. Okay, we're going to worry about that later on. Let's just look here at what we just figured out. Well, we learned that particles represent atoms. They also represent molecules or units. Just depends on what type of a substance you're talking about. And if we want to convert between moles and particles, or particles and moles, we are going to use Avogadro's number. 1 mole is equal to 6.02 times 10 to the 23rd particles. Go ahead and write that on your mole maps. And in fact, you can write the same exact thing off to the right-hand side of your mole map between moles of B and particles of B. It's going to be the same conversion factor, okay? Let's go ahead and write that, pause this and go ahead and write that down in both places on your mole map, between moles of A, particles of A, and moles of B and particles of B. Y'all set? Good. Okay, so we learned one conversion factor. Now what you guys are seeing is that there are 2 other conversion factors that are going to allow us to convert between moles and mass and moles and volume. And frankly, those conversion factors are actually used a lot more than Avogadro's number. Because if you think about a lab setting, like how often are we counting out numbers of particles of things? Like almost never. Now, when you guys are in grad school and maybe you have an electron microscope, you'll be able to see things at the particle level. But for us, we're going to be working mostly in the lab with mass and with volume. So we're going to need a conversion factor to take us in between mass and moles. So before we do that, let's talk a little bit more about particles and how much mass they have. So back to my PowerPoint here. Okay, so we learned that this was our conversion factor to particles, and it's based off of 12 grams of carbon. So it turns out that 1 mole of carbon has a mass of 12 grams. But if I have a mole of copper, its mass is like 64 grams. And if I have a mole of water, I have a mass of 18 grams. Even though this sample of carbon has 6.02 times 10 to the 23rd atoms, and this sample of copper has 6.02 times 10 to the 23rd atoms, and this cup of water has 6.02 times 10 to the 23rd molecules. They all have the same number of particles. But what's interesting is they all have different masses. How is that possible? Well, think about it. Different atoms are different sizes. Some atoms are light and some atoms are heavy. Some atoms are big and some atoms are small. So you can see that not only are they of different masses, but they also take up different amounts of space, even though they all contain the same number of particles. Let's look at another example. Here are a bunch of different substances. This is a mole of mercury 2 oxide. It's a mole of sugar, a mole of sulfur, a mole of the copper sulfate pentahydrate, a mole of copper, a mole of salt. They all have different masses and different volumes. Again, because of the size of the atoms themselves. So this amount of mass that each substance has when it makes up a mole is called its molar mass. So let's go back to our notes. We will leave our mole map for a minute and go back up here to talk about what molar mass is. So just like I showed you guys in that PowerPoint slide, a mole of carbon is 12 grams. A mole of copper, 63.5 grams. A mole of water, 18 grams. These are called molar masses. This is the amount of mass that exists. I don't want to say exists. That comprises one mole of any substance. And this mass is measured, of course, in grams. So our unit is grams per 1 mole. How many grams? It's going to be some number of grams per 1 mole of something. Now, where do you think we find this number? On the periodic table. It's the same number as the atomic mass. It's just that the unit is not AMU. Okay, so the unit on the periodic table is AMU for atomic mass unit. That is the mass of one atom. Take that number and turn it into grams. Now it's the mass in 1 mole of that substance. Okay, now what about if you've got a compound like water or carbon dioxide or diatomic oxygen? When you've got multiple substances making up a compound, you have to calculate the molar mass by adding up the individual molar masses of the elements in the compound. So for example, if I want to calculate the molar mass of carbon dioxide, I take the mass of 1 carbon, or 1 mole of carbon, plus 2 times the mass of 1 mole of oxygen. Again, because there's a 2 there in the compound. So that's a total of 44 grams per mole. Let's do another one together. Molar mass of nitrogen. Nitrogen has a molar mass of 14 grams per mole. I'm sorry, did I say the molar mass of nitrogen? I meant the molar mass of ammonia. Hopefully I said that. And ammonia, of course, is composed of nitrogen and hydrogen. Maybe I did say it correctly. Who knows? I'm going to multiply 3 times the molar mass of hydrogen, which is 1. And of course, that adds up to 17 grams per mole. So this is how we calculate molar mass. This would be a great stopping point, you guys, for you to pause and practice calculating molar masses on page 4, I believe, of your packets. Once you feel comfortable calculating molar masses, come on back to this lecture here, and we will talk about how we would use molar mass as a conversion factor between mass and moles, just like we used Avogadro's number as a conversion factor between particles and moles. Here we go. Let's say we want to know how many moles of carbon we have if we have 250 grams of carbon. So I'm going to start with my given value, 250 grams of carbon. If I want to know how many moles that is, I need the molar mass of carbon. And again, the molar mass is the amount of grams in 1 mole of that substance. It's always the amount in 1 mole. So I look on the periodic table at carbon. 1 mole of carbon has a molar mass of 12 grams. Now I knew to put my conversion factor in like this, so my grams of carbon can cancel. So my 250 grams divided by 12 grams. Again, this is one we could probably do in our heads here, people, but just in case, 250 divided by 12, 20.83. So my thing is not working. 20.83 moles of carbon. Now I have 2 sig figs here in my given value, so I'm going to round this to 2 sig figs, 21 moles of carbon. Okay, let's do another problem. The next problem says, what is the mass of 1.70 moles of sodium chloride? This time we're starting with moles, not with mass. 1.70 moles of NaCl. To figure out the mass of that, I need the molar mass of sodium chloride. It's the mass in 1 mole. So my 1 mole is going to go on the bottom this time. Again, remember, you're just going to flip your conversion factor depending upon whether you're trying to go into the mole or out of the mole. So the molar mass of sodium chloride, that's something I'm going to have to go calculate based on my values on the periodic table. Sodium, I believe, is 23. Doing this just off the top of my head. I don't even have a periodic table handy. Hopefully I'm right. And I think chlorine is 35.5. And so that gives me a molar mass of 58.5 grams per mole. Okay, so there's my 1 mole. So my 58.5 grams of sodium chloride goes on the top. Cancel my moles, multiply across, and I will get the mass needed. So 1.70 times 58.5. And we're going to need 3 sig figs here, so we're going to go with 99.5. 99.5 grams of NaCl. So there we have it. We have a second conversion factor that we can now use to convert into and out of the mole. And this one's really useful for us because I can measure grams in the laboratory. So if I measure grams in the lab, I know how many moles I have, or if I know how many moles I need, I can measure out that amount of mass. So let's add that to our mole maps. To convert between mass and moles, I'm going to use something called molar mass. And it's some number of grams in, you know what, let's keep it consistent. I put moles on the left for my other one. Sorry. So 1 mole equals some number of grams. And again, that number of grams can vary depending on what the substance is. So it's not a set conversion factor like Avogadro's number, which stays the same. It's some number of grams. And this number you're going to find on the periodic table. Okay, we are almost there, you guys. 1 conversion factor left between moles and volume. Now, On the top of page 5, you're going to notice that I stated that the mole volume conversion factor for our mole maps is really going to depend upon what state of matter our substance is in. So we're going to have different conversion factors depending on state. So we're going to start off by talking about the conversion factor that we would use if the substance was a gas. Now, gases, you guys, change their volumes at different temperature and pressure conditions. Like, think about it. If you heat a gas, it expands and takes up more volume. If you put a gas under high pressure, its volume will go down. It will take up less space under high pressure conditions. So the temperature and pressure matters when we're talking about the volume of a gas. So the number that we're going to use is at what we call standard conditions. Standard temperature and pressure is 1 atmosphere of pressure. That's our standard pressure. And 0 degrees Celsius temperature. Okay, these are our standard conditions. Under these conditions, 1 mole of any gas will take up 22.4 liters of space. This is what we call molar volume. But again, this is only true, you guys, at standard temperature and pressure. Okay, so like if I have a balloon with 1 mole of gas in it, any gas, doesn't matter what it is, and this balloon is at 0 degrees Celsius and 1 atmosphere of pressure, the volume of this balloon will be 22.4 liters. But again, if you were to heat it up, its volume would get bigger. If you were to cool it down, it would get smaller. And likewise, under different pressure conditions, the volume will change as well. So this is our conversion factor between volume of a gas and a mole as long as we're at STP. Let's practice. Oh, great. I didn't copy and paste the problem in. That was messed up of me, wasn't it? Well, we're just going to have to go with it. I'll have to write the problem in. The problem asks on page 5, what is the volume of 3 moles of nitrogen? So if I start off with 3 moles of nitrogen, I'm going to use my conversion factor. Again, the 1 mole is it's always 1 mole. So 1 mole of nitrogen occupies 22.4 liters of space as long as we're at STP. So my moles cancel out. I multiply 22.4 times 3. And I get 67.2, but I only need 2 sig figs here, so 67 liters of nitrogen. This is how we use molar volume as a conversion factor. Let's add it to our mole map. Where are you, mole map? All the way back down here. Okay. 1 mole of any gas occupies 22.4 liters, only at STP. Now, we're going to learn how to calculate volume under different pressure and temperature conditions in our next little mini unit that we'll do to get ready for AP Chem. And in order to figure out what the volume will be under different pressure and temperature conditions, we're going to use something called the ideal gas law. Don't worry about that now, but just throwing that vocab word out there so it doesn't sound so strange when we talk about it later. Okay, now if you're in CP, you can stop here. We don't need to talk about density. If you're in honors, keep going for a minute. Okay. So the problem is between, volume and moles, again, this only works for gases at STP. But a lot of the times in the lab, we're measuring solids and liquids in terms of their volume. And so if we have a volume of a liquid, like if I have a volume of water or a volume of mercury, and I want to know how many moles that is, I can't use this conversion factor. And I can't use Pivner, the ideal gas law, because these substances aren't a gas. So you'll notice at the bottom of page 5, it says, well, what do we do if we've got a solid or a liquid? So stay with me on your mole map for a second. If you have a solid or a liquid, what you can use is the density of that substance. Because density allows us to convert between volume and mass. Because density is equal to mass over volume. So if I have volume of a liquid and I need to get to moles, I can go from volume to mass using density, and then mass to moles using molar mass. Let's do a problem like that. And there is a practice problem on the bottom of page 5 below that gas conversion that we did. So I'll go back up to my gas portion. And again, I just totally didn't copy and paste these last two problems in here. My apologies. This problem says, how many moles of mercury are in 16.2 milliliters? So I'm in milliliters of mercury, which is a volume measurement, and I need to get to moles. But mercury is a liquid and not a gas, so I can't go directly down the mole map. Instead, I have to use density to go from volume to mass, and then mass to moles. So you can kind of see how your mole map is actually a map. So in order to use the density of the mercury, I first have to convert from milliliters to centimeters cubed. And luckily, 1 milliliter is the same as 1 centimeter cubed. Now I can use my density, 13.55 grams of mercury. This is a very dense liquid for every 1 centimeter cubed. Now I can use the molar mass of mercury to go from mass of mercury into moles. 1 mole of mercury has a molar mass of, oh shoot, gotta go look at my periodic table. 200.6. That's a big old molar mass as well. 200.6 grams of mercury. So now it's time to hit up our calculator here. Let's see. Okay, turn that guy on. 16.2 milliliters. I'm gonna multiply across the top times 13.55 divided by what's on the bottom, the 200.6, 1.09 moles. 1.09 moles of mercury. Now, if you're really curious, you're like, well, wait a second, Ms. Rivera. We've talked about states of matter for solids, and for liquids, we're going to have to use density. We talked about 22.4 liters as our conversion between volume of a gas and moles. We talked about Avogadro's number for particles. But there's another state of matter, which is aqueous solution. And how are we going to convert between an amount of an aqueous solution and moles? And we're going to get into that as well in that little mini pre-AP unit that I think we're going to have time to get to. In order to convert between volume of a solution and moles, we're going to have to use something called molarity. So molarity, which is a measure of concentration. So we're going to learn all about molarity, and we're going to learn all about the ideal gas law as additional conversion factors. But all you guys need to know for now is what we have here on our mole map. And you're going to use this map to help you figure out which conversion factors you need to use and in which order you need to use them in order to do whatever the conversion is asking you to do. So let's do one conversion practice problem together on page 6. These are mixed mole conversion problems. You know, I want to be able to look at my mole map at the same time. Okay, let's read the problem first together. It says, how many grams are there in 1.5 times 10 to the 25th molecules of CO2? So I want you to ask yourself, where am I on the mole map, right? I'm here in molecules, right? I'm given numbers of molecules. And the question's asking me how many grams is that? So I need to get over here to mass. And you have to follow the mole map. So I'm going to start here in particles. Again, molecules is a type of particle. And I'm going to convert into moles using Avogadro's number. And then I'm going to convert from moles into mass using molar mass. See how simple that is? Start with your given value. So our given value is 1.5 times 10 to the, 25th molecules of CO2. To go from particles to moles, I need Avogadro's number. The unit you want to get to goes on the top. 1 mole of carbon dioxide contains 6.02 times 10 to the 23rd molecules. And now I can convert from moles to mass using the molar mass of carbon dioxide. I want to get out of moles, so that goes on the bottom. 1 mole of carbon dioxide contains some number of grams. And again, I get that off of the periodic table. Carbon has a mass of 12. Oxygen has a mass of 16 times 2 for the 2 in the CO2. So that is a molar mass of 44 grams per mole. So my molecules cancel. Oops, I should have said molecules of CO2. My moles of CO2 cancel, and I'll be in grams of carbon dioxide. So one last calculation to do here together. 1.5 to the 25th times 44 divided by Avogadro's number. Boom. And I need to get to 2 sig figs, so I'm going to round this answer to 1,100 grams of CO2. Okay, so figure out where you're at on the mole map. Start with that value. Get to where you need to go by plugging in conversion factors, making sure that your units will cancel out top to bottom. So the unit you want to be in goes on the top. The unit you're trying to cancel out of goes on the bottom. Check your sig figs. Make sure you say what your substance is. And that's it. This is going to be a super important skill, you guys, because eventually we're going to take this across the mole map. So if you did not fill in the right-hand side of your mole map as well, go ahead and do so. You know, moles of B to particles of B, moles of B to mass of B, moles of B to volume of B. It's going to be the same conversion factors over there. There's just going to be one little magical thing that takes us between one substance and another. Can you predict what it is? We'll save it for next week. Good job.